This is lab 5 for the Slinky drop. The purpose of this lab was to analyze the motion of a Slinky as a point particle system that was dropped from static equilibrium and to see whether the bottom of the Slinky is stationary or not. We would do this by using Tracker to model the observed data and GlowScript to create the computation model. Then we will make comparisons to discuss the findings. The physics principles and concepts utilized in this lab include Newton's second law, the force of gravity, as well as drag force. We can use Newton's second law to help determine the relationship between the net force acting on an object and the change in the object's motion. Using Newton's second law, we will update the velocity and position of the data. To find the net force in the system, we have to add up all the forces acting on the system. For this particular lab, I had to calculate gravity, tension, and drag. For the first part of my lab, when the bottom of the Slinky is motionless, the forces acting will be just gravity and a tension force. Gravity, also known as weight, is found by multiplying mass by the acceleration of gravity, which when studying an object on Earth is 9.8 meters per second squared. The force of gravity is always in the negative direction, and the tension force is a force that is equal and opposite to the force of gravity. When the bottom of the Slinky is in motion, the forces acting will be only gravity and drag. Tension is no longer a force because there is nothing holding onto the Slinky from above when it is let go. The drag force is the force that acts in the opposite direction that the object is moving. The drag force in this experiment would be in the positive y direction because the object is falling in the negative y direction. The formula for the drag force is b, where b is the proportionality constant times the square of the magnitude of the velocity of the object. For my tracker analysis, I imported a sample video on YouTube of a Slinky being dropped. I assumed that the person in this video was dropping the Slinky from head height, and therefore I took the distance for the calibration stick to be from about head height to the torso as roughly 1.1 meters. As shown by the x and y position graphs, the bottom of the Slinky is relatively stationary until about 1.45 seconds, at which the graph starts to show a change in position. I created 3 arrows for this model. The first arrow is for gravity, the second is for drag, and the third is for the tension force. I could not find an accurate mass for the Slinky, so I left it as a default value of 1 kilogram. Next, since I am only going to be modeling the motion of the Slinky in the vertical direction, I only inputted the initial y position, which was negative 0.529 meters. Since the Slinky is dropped from rest, the initial velocity is just a zero vector. The acceleration due to gravity is given by the value 9.8 meters per second squared. For the proportionality constant, I had to estimate it by inputting different values until the final position of the predicted model matched the final position observed from Tracker. Doing that, I got b to be about 53.8. I then created 2 while loops. The first loop represents the bottom of the Slinky while it is motionless, which occurs for about 1.45 seconds. The net force during this time is the sum of the force of gravity and the tension force, which is equal and opposite to the force of gravity. I then used Newton's second law to update the velocity and position of the object using the following formulas. The last thing I did was to make sure that my arrows corresponded to their respective forces. So arrow 1 represents the force of gravity and arrow 3 represents the tension force. The second while loop represents the bottom of the Slinky while it is in motion. The loop is essentially identical to the first, except the net force this time is the sum of the force of gravity and drag. And arrow 3 from before is replaced with arrow 2, which represents drag. Running the model, we see that initially when the bottom of the Slinky is stationary, the forces acting are tension, which is the green arrow, and gravity, which is magenta. And then when the Slinky is dropped and the top mass reaches the bottom, we see that the forces now are drag, which is in blue, and gravity, which makes sense since there is no longer a force pulling at the Slinky from above. In the graph displaying the observed and predicted motions, we see that there is some variation which can be accounted for by how difficult it was to manually track the point mass in Tracker since the Slinky moves very slightly from time step to time step. Overall, though, the observed and predicted follow the same trend. The bottom of the Slinky is motionless due to the tension pulling up, which balances the force due to gravity pulling down. It is not until the moment that the Slinky is fully compressed that it falls with the acceleration due to gravity. In other words, the top of the Slinky collapses and the coils begin to slam into each other, and so the bottom coils remain at rest until the top crashes into them. If we were to have used a multi-particle system, we would still get the same concept that the bottom of the Slinky stays stationary until it gets fully compressed. However, as a multi-particle system, we would model the system as a chain of multiple masses connected by massless springs. All the connected masses start to move down and get compressed, and when they all meet at the bottom, that is when the bottom of the Slinky is no longer motionless, at which the whole system begins to fall downwards with an acceleration due to gravity as shown in the following picture. The ways in which this lab could have been improved include having a more accurate model. Tracking the point mass for the Slinky was difficult due to video quality as well as not being able to clearly distinguish where the center of mass was for the Slinky. Furthermore, at the beginning I stated that I made an assumption that the person in the video was dropping the Slinky from head height, but that may not be true, and so the scale of my model is most likely not accurate. Furthermore, for the proportionality constant, I had to estimate it rather than mathematically calculate it using a formula. Overall, applying Newton's second law and using the computational model, we were able to analyze and observe the net forces acting on the Slinky as well as its change in position, which allowed us to answer why the Slinky was stationary until the moment that the spring was fully compressed.